Hi everyone. Today I'll be presenting George Shibenko's seminal 1989 paper. It was called Approximation by Superposition of Sigmoidal Functions. And this paper is not just seminal, it's very foundational because it kind of established the universal approximation theorem. And we will kind of get deep into it, but it was the paper that gave some theoretical justifications of why even simple neural networks can be very powerful. And we'll go through the main result. We'll see the very nice manipulation that they do to get the proof, and also we'll see the main concepts that are kind of try to relate to the concepts we did in class, but from a slightly different perspective. um, Before we rush on to the main results of the paper, I'd like to go through the motivation of why I select this paper and also some slight historical context. So kind of the central question around around neural networks in very early days was it was like a very simple question, that what functions can these model even represent. um, and before 1989 the understanding was not very broad. We knew from Nilsson's work from 1965 that neural networks can solve basic classification problems. For example, if you have a finite set of points, they can be classified using a network. But there was no rigorous general theory for the same results. There were empirical results, and they were coming close with, I think, the MNIST data set in Jeffrey Hinton's group, their efforts in the same in 1980s. But there were no rigorous proof of some general function approximation. And what Chemenko did was it proved that a single hidden layer with a neural of in a neural network is sufficient to represent any continuous function, and also under some assumptions, and it also established kind of the minimum conditions that you need on activation functions. I'll define all of that later. And it also kind of connected neural networks to the approximation theory that was there before that, which is also what we studied in the course. So basically, what a neural network um, is it's a very standard architecture, and I'll define this architecture for a single hidden layer in a feed forward neural network. I'll define what all of those terms mean. I say that my output g of x is nothing but a weighted sum, and inside the sum we have n different terms, one for each neuron in the hidden layer. So that's the terminology. And for each neuron, we have an input vector x. It's projected by a weight matrix wj, and it's shifted by some bias theta j, and then passed through a non-linear activation function, which is what sigma is, and then finally it's scaled by some output weight alpha j. Everything is summed up. uh, Now, the only thing abstracted out here is the sigma j, which is the activation function. And for this simple architecture, to kind of approximate different classes, different kinds of functions in input x, what kind of properties does um, sigma need to have? Or rather, it can be framed as a question: given a sigma, what kind of functions can gx express? So in general, this is something that we also defined in pack learning. We want to see what the expressivity of a hypothesis class is. um, so some quick definitions: I say that a function sigma is sigmoidal if it is 0 at input minus infinity and 1 at input infinity, and it's continuous. It does not have to be continuous, but for this paper the assumption is that it's continuous. And I say that sigma is discriminatory if for so there's some terms that would need definitions, which would stretch this a lot, but I'd like to give a broad definition. You say that if you take any finite signed Borel measure mu on a unit hypercube, I'll try to define what that means. Um, right. So what you can do is you can think of this mu as kind of a way to assign weight or mass to different regions. And I say that the integral of sigma against this measure is always kind of zero. Then for all possible linear transformations of input, the only conclusion is that the measure mu must have been zero all along. Um, This is what it's trying to broadly say, and it intuitively means that the function sigma is rich, but it's also varied. It can't be perfectly cancelled out by any non-trivial weighing scheme, and it can effectively help you discriminate between a zero measure and any other measure. Now, what zero measure is and what Borel's measure is would be too long for the discussion here, but we can just kind of assume right now that that's how a discriminatory function is defined. um, we also have to see some general definitions of function spaces and norms, which will be helpful for the proof later on. Uh, I'll define what the broad playing field is. The space of functions that we want to approximate is, let's say, CIN. These are all continuous functions on IN, which is again the hypercube that we defined above. Um, so IN is the nth dimensional unit hypercube, and the way we measure closeness is with something called a supremum norm, which is sometimes also called, I think, the uniform norm. And you mean that for a network G. So I'll go back to the G that we defined. You say that for a network G to be a good approximator of function f, um, you try to say that the absolute divergence, which is nothing but gx minus fx, must be small, and that should be true for every single point in x. So when you take the supremum of something like that, you try to look at the max possible error instead of the instead of, let's say, the average error. So it becomes kind of like a stronger condition. um, you define S as the set of all possible functions that a network can produce. And the ultimate goal that we broadly have is to prove that the closure of S, let me see if I've written that. Yeah, we need to prove that the closure of S is nothing but the target space. Now, closure is in general all possible functions that I can represent by, let's say, linear combinations of functions um, in a set, and I say that that closure, or all possible functions that can be spanned by S, is nothing but the target space, which is all possible continuous functions on IN. Uh, or as this definition down here says, that for all functions in my target space, I can say that there is, and for any arbitrarily small epsilon, I can say that there exists an approximation of it with, let's say, a sufficiently large network such that it's arbitrarily close to my function f. So the main function, the main theorem, universal approximation theorem, it said that if you have sigma, which is any continuous sigmoidal function, and then the finite sums that we define, which is nothing but our single hidden layer network, they are dense in the space of continuous functions on the unit hypercube, which broadly means that no matter how complex or how, let's say, wiggly a continuous function is, as long as it's on a compact set, uh, I'll define what that means. But as soon as it's on a compact set, there exists a shallow network that can approximate it to any desired degree of accuracy by just adding more neurons. By shallow, I mean the depth is one. So in general, when you have neural networks, you can stack the layers. Some output from one hidden layer can enter to another. But we're saying that for a shallow network, just by increasing the width of it, we can approximate any function to any arbitrary um precision, as the significance says. This was kind of the bedrock for why networks can work on complex regression as well as classification. But I'll move on to the proof now, which would help us kind of get more intuition on what I'm trying to kind of say. Um, the proof is elegant, and it relies on some analysis from, or rather, a lot of functional analysis. And we'll look at the proof in three ways broadly, or rather, three steps. First would be that we'll have to show that sigmoidal property implies the discriminatory property, and we'll have to show that any continuous sigmoidal function satisfied the condition that we defined earlier. Um, For this, we'll be using things like bounded convergence theorem and some Fourier analysis. The next step would be to prove a very general statement that any continuous discriminatory function can generate a dense subspace. I'll assume that everyone knows some basic linear algebra, so I won't have to define subspace again. But it's a very classical way to prove such an argument, and it uses something called the Hahn-Banach or the Hahn-Banach separation theorem, um, and the Rees representation, which helps converting functional to measures, but that's not very relevant to be honest. And then step three would be to kind of combine one and two to get our main result. But broadly, we'll say that if a sigmoidal is discriminatory and discriminatory can imply density, then sigmoidal can imply density, which is a very logically following chain, right? So for the first part, the setup is that we assume we have a measure on mu, and that makes the integral of our sigmoidal function zero for all possible weights w and biases theta, and we need to show that this forces mu to be zero. So the measure comes out to be zero, and that's what we want to that's what we want to kind of show. And the main idea is to see what happens when I make my sigmoidal infinitely steep. So what I can do is I can scale its input by a large parameter lambda. I can say there's a very large lambda. As lambda goes to infinity, the smooth sigmoidal function kind of sharpens onto a very steep step. And we can do this by scaling its input by a very large lambda. And if the function kind of becomes 1 when its input is any positive value, and it becomes 0 when the input is negative. And this kind of sigmoidal is sometimes also called a perceptron. And we'll see that this network is also nothing but a single hidden layer perceptron, and you can also extend that to commonly known as MLPs or multi-layer perceptrons. But yeah, that's the broad observation, and scaling sharpens the sigmoid into a step function. And I think in most signals and systems courses, we'll see why Fourier will come, because step functions can be well analyzed using a Fourier transform. But yeah, so for proving that they're discriminatory, what we'll do is we'll formalize our intuition, because since a sigmoid is bounded, we can use the Lebesgue bounded convergence theorem, and we'll help it to pass the limit as lambda goes to kind of infinity inside the integral, and we'll say that our integral, which we know is zero, um, converges to this new expression as we can see. And this expression is nothing but a weighted sum of measure of the hyperplane itself, and and the measure of the open half space. Now again, it's a lot of terminology, but half space because it takes all values greater than zero, and it's the hyperplane because it's the complete set of x's that the hyperplane that makes it zero, or the solution of x, um, which is nothing but the transpose of weight inverse times, or the negative of transpose of weight inverse times theta or cross theta. Um, but yes, anyways, since this holds for all possible uh, phi's, we'll have to say that as we take phi to minus infinity, this term has to be zero, else the final thing would not be zero for any value of mu. And similarly, if I take it to positive infinity, I know that this value has to be zero for any possible value of this. Or maybe I said the opposite, but that makes sense, right? So you kind of conclude that measure of all such half spaces is nothing but zero. And how do I go from this half space thing to a zero measure thing? I say that yeah, I'll define this functional which maps so let's start by assuming that an w or the weights are fixed. So I define a linear functional, and it integrates any function h of the projected input against our measure mu. And from the previous slide, we kind of know that f is 0 for indicator functions of half spaces. um, by linearity, it also means that it has to be zero for any simple function that I have, which is nothing but the sum of the indicators that we discussed above. And since simple functions are dense in the space of all bounded functions, this means that function f must be a zero function. This argument is very intuitive if you kind of think about it. This kind of means that if f is zero for all bounded functions, it must be zero for, let's say, sines and cosines. Then my integral function for s plus ic is precisely, which is the definition of the Fourier transform of the measure mu. Uh, so we have kind of shown that the Fourier transform of mu is also zero everywhere. And by the uniqueness property of Fourier transforms, that Fourier transform is a unique representation, we can say that the transform has to be zero. The original measure must also be zero. And this was kind of the proof of the first lemma that we wanted. So it kind of meant that sigmoidal functions are kind of discriminatory, and I'll quickly go over the three parts. So I first show that sigmoidal is discriminatory, so that's my goal. So for that I define this mu. I say that the integral with respect to mu is nothing but zero, and then I say that, okay, this, if this is true, then this will remain true if I take this lambda arbitrarily large. And this was helping us kind of approximate some half space indicators. And then I said that, okay, let's define this h and big pi, and as lambda was tending to infinity, we got some nice arguments that measure of both of these have to be zero, the hyperplane and also the open half space. And using, so I mean, you can keep this arbitrary as less than zero, greater than zero, that doesn't matter. And the hyperplane is where it's exactly zero, and for both we proved that it's zero. Therefore broadly everything had to be zero, but we did it in a better way. We said that we go from half spaces to getting that zero measure. For that we defined this linear functional L, and we kind of showed that that it has to be zero because we put in this substitution, and we said that that is nothing but the Fourier transform. And if the measure Fourier transform, the measure is zero everywhere, then by uniqueness we can say that mu is zero, and that proved things for us. So now we say that, okay, sigma is discriminatory. Then we want to show that the closure of this S is nothing but dense in my target space, right? And we'll take contradiction. We'll say that there is some function which does not follow the same. So that's how the proof will broadly go. And it's a hard argument to see from functional analysis, but it's very intuitive if we kind of think about it. Let's assume that our network space that we've defined S is not dense. That means there should be some continuous function that we can't get arbitrarily close to. So if S is not dense, its closure is a proper closed subspace of a total space Ci. uh, that is clear, right? Because at best when it's dense it can be C, because C is the big space. And I'm saying that no, that's not true by contradiction. Therefore S has to be a proper subspace of C. um, by proper subspace, it's that there is at least one function which is not in there. um, and we'll again use the no, not again, we'll use this theorem called Han-Banach theorem, and it's kind of very commonly used thing in functional analysis. And it tells us that if I have a proper closed subspace, there must exist a non-zero bounded linear functional L that is zero for everything inside that subspace. uh, and you can kind of try to imagine that it's very intuitive. And this is kind of a very strong example of the primal dual witness argument. Yeah, which is kind of like you fix one and then you try to play around with other things. You say that there exists a bounded linear functional L which maps from your functions in C to some real value where L is not equal to zero, but you say that for all such S, L is zero. And you're saying that there is some function for which and it has to be a proper subspace. If it's not, then this does not hold. But yeah, um, we'll use the rise or the Rees representation. And it'll get a little complicated, but I'll try to keep it well explained uh, as much as I can. So So you say that from Han Banak you got that there is some abstract functional L, and the Rees representation will help us actually formulate that. We say that if there is any functional L on the space of continuous functions that can be represented as an integral against some finite signed Borel measure mu. Uh, so you say that you can represent a functional L by taking an integral over some Borel measure mu on the unit hyper cube, uh, and that will give us some nice properties. We have to just kind of connect the dots right now. So I say that we know that L is zero. That's something we assume from Han Banash, and we now need to figure out what that L has to be. So we know that every function s that we have, uh, that is going to be zero everywhere. So we say that the integral must be zero for every function which has this form sigma and a linear transform on theta, sigma plus linear transform on the input x, and this is true for all possible weights, for all possible biases. Uh, and we know that sigma is discriminatory, so we know that mu has to be zero, which implies that your L will also be zero. But because you start with a contradiction that is not zero, you directly get a contradiction. So just I'll kind of try to summarize it. We start by saying that, oh, let's assume that any function cannot be approximated using using a weighted sum of these sigmoidal transforms to all linear transformations in X. Uh, and I defined a space spanning all such functions, and I said that the closure of this set S is not equal to C, therefore this set is not dense in C. And to prove it, I said let's assume that uh, that this is not true, it's not dense. Therefore by simple construction we can say that C is larger, therefore S has to be a closed proper subspace of C. When it's closed proper subspace of C, we from Han Banash we got that there is some linear functional L, um, and L is not equal to 0, but L but there is a uh, but L is such a function that for all s's it's zero, and it's not equal to zero because you're saying that there exists some function f which is in C but not in S, and on that function it does not need to be zero, right? And the primal dual witness argument comes in here because we are saying that we are kind of uh, we're saying that there is existence of a witness which is nothing but the functional L that kind of separates the subspace from the rest of the space, which is kind of helping us prove that it's not dense. um, yeah, the next argument was let's try to use some representation which can help us get any functional L, and I said that any functional L can be constructed using this integral over this unit hypercube, and then uh, there's this function for some function h. I can take its integral with respect to the measure, and I say that this can represent any functional L. And then I said that I know that my hx can be represented by whatever the representation of my single hidden layer network was. And then I said that for all weights and for all biases, my measure of sigma is nothing but zero, and therefore I said that the value of L is zero, and which contradicted the fact that uh, L is not zero, and that kind of gives us the whole proof, but we will still see what can happen. Uh, from lemma 1, we kind of know that any continuous sigmoidal function is discriminatory, and from lemma 2, we know that any discriminatory sigma generates a dense subspace. Therefore, all the set of networks which can be generated by any continuous sigmoidal function is dense in the space of continuous functions. And that's broadly the proof. The universality of this is very powerful because it doesn't just work for one specific sigmoidal function, but it works for any function that has this S shape kind of property. Like as they said, sigmoid or tanh or arctan, which you can obviously scale to get whatever you want. Uh, now, what are the implications? This is important. Um, So the key motivation initially was classification. So let's see what this can be done. I'm saying that we can approximate any decision function, one with even very complex disjoint decision boundaries. And the proof sketch that we use is very interesting, which gets us to the final form of the universal approximation theorem. We use Leuzen's theorem, which is a result from measure theory, and it states that any measurable function. Now, we talk about measurable functions by so whenever in this context we talk about measurable functions, just think of normal functions that you see in real world. Uh, just think every decision function that you want to use is probably going to be a measurable function, and a measurable function is almost continuous. It doesn't have to be, so kind of the Leuzen's theorem says that we can find a continuous function h that is equal to our decision function for everything except on a set d of a arbitrarily small measure. Um, so I'll try to explain what that broadly means. I know that my h is continuous because that's how we constructed it. We can use our approximation theorem to say that we can find a network G that approximates h as closely as we want, and because of that, G will be a great approximation of our original function f on that very large set D. In other words, we can approximate kind of any decision boundary with an arbitrarily small set of badly misclassified points. So I say that there is a finite measurable partition of I, and for any epsilon, there is a G such that a set D, which is a subset of I, with its measure greater than 1 minus epsilon, we can get a G which is arbitrarily close to F by epsilon, and that is true for all x's in this D. I think I meant when I said that D is the misclassification set, D is the classification set, not misclassification one. Misclassification is the arbitrary error that we're assuming, right? Uh, Now, I'll try to connect it to things we did in class. First is the argument of expressivity versus learnability. So Chebenko's theorem is about expressivity. It proves that a hypothesis class is rich enough to kind of represent very hard functions, but it does not help us guarantee learnability at all. And actually, that was a very very big thing, uh, which was stuck because there was a paper and it proved that you can never learn neural networks because there's too many local minimas and you're bound to get stuck. And at that point uh, uh, there were no good optimizers which had these properties like momentum, which can help you get rid of local minimas, like um, yeah, exactly, having velocity and momentum and stuff, which the which optimizers right now have, and they don't have really good convergence guarantees, but empirically they work very well. But again, what I meant was that the function exists, but it can be in theory impossible to find that with a final sample of data, right? From kind of like a VC dimension perspective, the class of all single hidden layer networks is um with let's say an unlimited number of neurons has an infinite VC dimension, which is which can be seen very trivially, and this kind of means that a standard back learning framework cannot be applied directly, and to get any kind of generalization guarantees we need to restrict the class. For example, let's say I have finite neurons, or let's say that my weights are bounded. In such cases, we can kind of get some argument for pack, but with like an infinite VC dimension, which is what you're kind of generally assuming with this single hidden layer network, we cannot do anything for getting some pack learnability guarantees. This theorem does not talk about Rademacher complexity of the function class, and for any kind of data dependent generalizations, we know that we kind of need it. So, and actually, I think this is a very nice discussion on regularization as well. We kind of need regularization not just as a nice trick, but it's kind of essential to getting control over the complexity and kind of preventing overfitting, which can happen if your class, let's say, hypothesis class is big enough. And uh, and yeah, I mean, we can get into kind of like the details of how that exactly helps, um, but it trivially follows from the proofs that we did above. Um, Now, what this theorem did not tell us, and what people later on or before this did, was it had no information on what the size of the network will be. The proof is not by construction, it's an existence proof. Therefore, it uses like the axiom of choice, and that specific step which uses that was Hanmanak. Um, it does not tell us how many neurons that we would kind of exactly need. In the worst case, this can grow kind of exponentially with the input dimension, for example, which is called the curse of dimensionality. And Later in 1993, 4 years later, Barron kind of showed that the number of neurons you need scale by 1 by under root n for very special function classes. Uh, which was the special function classes were actually smooth function classes, mean that which mean that you can I think bound the derivatives, you can say, for any 2 points on the function fy minus fx upon y minus x is bounded by some epsilon. Um, yeah. Oh yeah. So okay, now the next thing about training, we can say that there's no algorithm which is which can be constructed directly from the proofs that we did above, which can figure out the weights and biases. Gradient descent is something used in practices, but it's a big challenge, as I said. Even right now, we don't have guarantees for something like Adam. This also doesn't tell us what number of samples we broadly need for getting approximations. Uh, there were other works, and this work was, I think, one of the first papers, and it kind of opened up the doors for several other interesting proofs that came, uh, and also some seminal papers on learnability of neural networks. But yeah, so Hornick and some other people showed that the activation function doesn't need to be sigmoidal. Any non-constant, bounded, and continuous function will do. Actually, the proof uh, very interestingly follows that you can write any such function using sigmoidals, and then it's a two hop argument. Sorry. Uh, and later there was again Leshno, which provided that a network is kind of universally approximated if and only if its activation is not a polynomial, and that's what they proved. Uh, and this was kind of a very big result, because you can say that every modern activation like ReLU or the ones we use right now, or even a perceptron, is a universal approximator. And people have been extending this theory to different kind of spaces, like LP spaces. There is uh, Barron had a paper in which he provided bounds on the approximation rates, not just the approximation. Oh yeah, so he had on some function it kind of provided bounds on the approximation rate, and now we in general in modern approach to this, we focus on trade-off between the depth and the width. Um, in practice now we look at networks with a lot of layers, not just width. We use ReLU over sigmoids and again vanishing gradients and thing. All these things can be discussed. We use over parameterization, and I think this is a very sorry, over parameterization is a very important and interesting argument. Um, if anyone wants to check out this thing called double descent, and the variance versus bias trade-off that people had thought for a long time was actually false. uh, People always assume that over parameterization means overfitting and harder to learn, but that was not necessarily true. As you scale networks, uh, you realize that having a very over parameterized network can actually help get a more generalizable or generalized function for some approximation rather than a smaller network. So for example, you have 5 points and a polynomial of degree 5. uh, Polynomial of degree 5 will perform good. Let's say you have some noise. Polynomial of degree 6 will perform bad. 7 verse, 8 verse, 9 will maybe perform a bit better. 10 may actually perform better than a 5-degree polynomial, even though the hidden place where it came from was 5 degree. But so what I in general mean is that with neural networks, there were a lot of complexities which arose because you had some guarantees on it, which started from this paper. And there's a big gap uh, between theory and what people actually do in reality, and that kind of comes from yeah, exactly, over parameterization kind of helped with some optimization, because in high dimension spaces all the local minimas kind of started to disappear. uh, Deeper networks were easier to train because the gradient could flow better, and there were some inductive biases. uh, like in CNNs, you had translational invariance. In transformers, uh, you had the dense attention passes, and they were kind of crucial for some real world data which had long range dependencies, or which had some symmetries which had to be exploited. But yeah, I think I've repeated all of this, so I won't go into everything again. But some connection to statistical learning theory, that expressivity is not learnability, and we kind of need VC and Rademacher for having good backbounds. Um, Again, so proof techniques were really interesting, and I specifically wrote this page because I learned about functional analysis and measure theory and all of these when I first read this paper. Um, so in I'll discuss future directions, and that's all. Uh, so still a lot of latest architectures do not have good guarantees on them. So for example, I'll give example of GNNs because that's of my interest. Uh, there was a paper by uh, Stephanie Jegelka, and she proved that GINs, which is graph isomorphism networks, are as representative as a message passing network can be. And she also showed that it is at most as good as something called the 1WL test. And people have come up with various architectures which are not bounded by one WL. Like there is this paper by Amir Kloperson's group called Tree GNN, I think. There are papers um, by Johannes Lutzer, Path GNNs and stuff, which again are not bounded uh, by one WL. But still, we don't have proofs on what are they actually bounded by, what's the representative, how representative they are. But yeah, I think still there's a lot of research going on in in how can you have sufficient representativeness while understanding what specific properties you want. For example, permutation invariance in GNNs, or different kinds of invariances that people are looking in geometric deep learning, but still a lot of architectures don't have exact guarantees. Uh, these would be some things which I think are very interesting to follow up on. Thank you so much. I think I extended more than I was supposed to, but I hope this helps. And please feel free to send me a message on WhatsApp or email for any questions or any confusions or anything that I said wrong in my presentation. Thank you so much.